We assume the universe can be understood, that, with enough data, better models, and more powerful tools, everything will eventually make sense. This assumption feels natural. After all, it has worked before. We decoded gravity. We mapped planetary motion. We explained stars, galaxies, and cosmic expansion. Each success reinforced a belief that the universe is not only governed by rules, but by rules we are capable of fully grasping. But extreme worlds challenge that belief, not because they are mysterious, but because they remain resistant to simplification. They don't fit neatly into our frameworks. They don't reduce cleanly into equations we can trust. Even when we observe them clearly, they refuse to behave intuitively, and that forces an uncomfortable thought. What if the universe is not optimized for understanding? What if it is not structured to be fully predictable, fully compressible, or fully explainable by any single framework? Our models work best in calm regimes, where forces are linear, where interactions are limited. But the universe is not obligated to remain calm. It allows complexity to stack, feedback loops to persist, extreme states to become permanent. In those regimes, prediction becomes fragile. Small uncertainties amplify, long-term outcomes diverge, and explanation loses clarity. This doesn't mean the universe is random. It means it may be fundamentally more complex than our tools are designed to handle. Extreme planets exist at this boundary. They are not hidden, they are observed. Yet they remain resistant to full understanding, not because we lack intelligence, but because we may be confronting systems that do not simplify. And if that is true for planets, it may be true for much more. Prediction is one of the greatest achievements of science. When we can predict something, we feel we understand it. We can calculate where a planet will be in 1,000 years. We can estimate the lifetime of a star. We can simulate the evolution of entire galaxies. These successes created a powerful expectation that with enough precision, the future becomes knowable. But prediction has a hidden weakness. It works best when systems behave smoothly, when cause and effect remain proportional, when small changes produce small outcomes. Extreme systems don't behave like that. In extreme regimes, prediction becomes unstable. Tiny uncertainties grow. Feedback loops reinforce. Deviations, long-term outcomes diverge rapidly. This is not a failure of mathematics. It's a property of complex systems. Extreme planets sit exactly in this zone. Their behavior is shaped by interactions that cannot be isolated. Rotation affects heating. Heating affects chemistry. Chemistry affects structure. Structure feeds back into rotation. Each variable depends on the others. This creates a system where prediction does not converge. Even when the rules are known, the outcome remains uncertain. And this is where intuition breaks down. We assume that better data will fix the problem, that higher resolution observations will reduce uncertainty, that more powerful simulations will restore confidence. But in some systems, more detail reveals more complexity. Instead of clarity, we get sensitivity. Instead of certainty, we get divergence. Extreme worlds don't hide information. They expose too much of it. They operate in regimes where long-term prediction is fundamentally fragile. This forces a difficult realization. There may be limits not just to what we know, but to what can be reliably predicted at all. Not because the universe is random, but because it allows complexity to accumulate faster than prediction can control. In these regimes, understanding becomes local. We can describe what is happening now. We can explain why certain states are possible. But we cannot confidently project far into the future. And that challenges a core assumption that science progresses toward total predictability. Extreme systems suggest something else, that beyond a certain level of complexity, knowledge does not eliminate uncertainty. It only reshapes it, which means that some aspects of the universe may always resist long-term explanation, not temporarily, not until better tools arrive, but permanently. And if that is true, then the goal of science may not be to fully predict the universe, but to understand where prediction ends. If there are real limits to prediction, Uncertainty is not a flaw. It is a feature. This forces a shift in how we think about progress. For a long time, we believed science moved toward a final picture, a complete description, a unified explanation. But extreme systems suggest something different. That understanding may be layered, partial, context-dependent. We can know how a system behaves without knowing exactly how it will evolve. This is not weakness, it is realium. To be simple enough for complete mastery. Predicted and compressed into equations. A boundary that defines where different kinds of knowledge apply. On the other, interpretation matters more. Science does not end at that boundary. It changes language. But if we accept uncertainty as part of reality, we gain something else. Without losing what makes them work. And that humility is not the opposite of science. It is a requirement for it, because every time we assumed the universe would eventually become simple, it responded by revealing another layer of complexity. Another exception, another reminder that understanding is not ownership. It is relationship. And as we continue to explore worlds that resist explanation, the real question is no longer whether we can fully understand the universe. It is whether we are willing to accept a universe that remains partially beyond us. In the next video, we'll look at how these limits shape the future of discovery, and why the most important breakthroughs often begin with admitting what we don't know.